Today we're going to talk about the nomenclature of complex ions. Complex ions, or coordination complexes as they're sometimes called, contain species that have coordinate covalent bonds. The coordinate covalent bonds are similar, they are covalent bonds. They do involve the sharing of electrons. But what happens is the pair of electrons that are shared all it comes from the same donor atom. So what do we mean by that? Well, you'll have something like, for example, this species down here, ammonia. Well, if you notice, if you draw the structure of ammonia, over on the side over here, there's a lone pair of electrons. And that lone pair of electrons can attach onto another species. Often that other species is a metal cation. We'll see that happening, and those are the types of things that we're going to learn how to name. When we have these species that have this lone pair of electrons or these donor atoms in them, they're called ligands. Ligands are usually neutral, like ammonia is, or they're negative, like nitrate, for instance, would be, because they have these extra electrons. Now, some of the common ones that we'll see a lot are ammonia. Now look at water. Usually they'll write the atom that is the donor atom that has the lone pairs of electrons on it first. So you're going to get water looking a little funky here with the OH2 instead of the H2O. Notice some of the names for them when they're named as a ligand, and we're going to see this in a moment. Amine and aqua. Amine for ammonia, aqua for water. Some other common ones, chloro for chlorine, or chloride, fluoro for fluoride, cyano, hydroxo, bromo is common for bromine. So you'll see several of these as we learn how to name these complexes. Now again, this complex ion is an ion that has a metal cation in the center, and a very common example of that is the copper 2+ ion. And what happens is that these donor atoms from these ligands come in and attach to what we think of as holes around this copper cation. So in will come an NH3 with its donor pair of electrons, another NH3 here, another here, another here. The number of donor atoms or species with donor atoms in them, or ligands that will attach to one of these cations, is called the coordination number. So for instance, this particular species would have a coordination number of 4, since 4 ammonias can attach around that copper cation. And that entire thing, that entire sphere, if you will, of the copper with the 4 ammonias, and I should have put a 3 here with this one, that's called the coordination sphere. When you see it in a I guess you can't really call them compound, but when you see it in the formula, they're usually separated from the rest of the species with brackets. Now we have 2 different kinds of ligands. Ligands that have one donor atom are said to be monodentate, and we think of these little pairs of electrons here. I guess you can think of as kind of vampire teeth. Dentate meaning bite onto. So if they've got one bite possible, then it's said to be a monodentate. If it's got more than one place that it can bite onto something, it's called a polydentate. And if we have polydentate ligands around a metal cation, for instance, we call them chelate complexes. Now, it's important to know about these chelates, these polydentates, because they are often used to treat things like heavy metal poisoning. When a child, for instance, eats some kind of paint or something that contains lead, we can give them one of these chelating agents, and they can take that chelating agent, it will go through their body, it will bite onto the lead cation, and then make this chelate complex that the body can't use, it can't attach to anything, so the body sloughs it off as waste then, and we can get rid of that lead poisoning, which has some pretty horrible effects on children whenever they get that. So when we name cations, I'm going to read some rules, not to confuse things. I'm going to read them pretty quickly. They're not going to make a lot of sense until we actually apply them. But this time I actually do want to talk about the rules because they're kind of different. Ligands are named in alphabetical order. We'll see that in a moment. The numbers of monodentate ligands, we use common prefixes to show those. Di, tri, tetra, penta, hexa, etc. Now, if we see polydentate ligands, and I'm only going to ask you to know these three. Ethylene diamine, which has a symbol of En in parentheses, both lowercase, notice. Oxalate, OX in parentheses. EDTA, which is ethylene diamine tetraacetate, EDTA in parentheses. Those are the only three that I'm going to ask you to know. But if we have those in the chelate or the complex, then we're going to use some weird prefixes to indicate those numbers: bis, tris, tetrachus, pentachus, and hexachus. There's probably a reason for that. I don't know what it is, but it makes some kind of cool names. So we'll see that. Now, my favorite structure is for EDTA. Look at EDTA here. It looks like a crab biting onto things, but that's what will actually, like I said, bite onto those metal cations and attach to them. Just some examples showing here of some of the ligands that you'll see. Some bidentate ligands like the ethylene diamine we were talking about. The oxalate ion. Carbonate is actually a bidentate. The ethylene diamine tetraacetate is actually a hexadentate, so that one will bite like crazy. So those are some examples of those. When we name negative ligands, we end them in O, like sulfide becomes sulfido, carbonate becomes carbonato, sulfate becomes sulfato, nitrate, nitrato, thiosulfate, thiosulfato. Neutral ligands, we often have to memorize those, and you can see examples on the previous page. Things like ammonia becomes amine, water becomes aqua. You'll be surprised how quickly you'll get used to that as you work on the assignment. It doesn't take long for us to pick up those names at all. We name the metal last in the coordination sphere. We'll use the Roman numeral if we need to. And we don't leave any space between any of the coordination spheres, so sometimes the names get pretty darn long. And any portion outside the coordination sphere, we just name like we always do. So let's look at some examples. So these are all cations, so the coordination sphere is going to go first, and you can see the coordination sphere is blocked off with brackets. We name the metal last. So we name whatever's with it first, and it looks like in parentheses we see what ligand. So that you can get used to this, have that out so you can see the chart and pick these out as we go, and don't just listen to me say them. You're not going to find them yourself, be able to find them yourself if you always just listen to me do this. So if you look back on the chart at the beginning, you'll see that NH3 is amine, and since it's in the monodentate list, it's going to be named with regular prefixes. So it looks like we've got two of them, so it's diamine. Remember, we do not leave spaces in the coordination sphere. So since that's all that's in it besides the metal, we can go ahead and just name silver, diamine silver. Then you're going to name the metal just like you would if it was in a regular compound. If it needs a Roman numeral, you're going to give it one. If it does not, then you're just going to let it go. And just leave it without one. Silver, remember, is one of our always trues. It's always a +1, so we do not need a Roman numeral with it. Although I have seen people do it, even the AP test, I've seen put a Roman numeral 1 after it, but you do not need one for silver. So diamine, silver, and then we name the rest of it as we normally would just chloride. So we look at the next one. Mark off the coordination sphere. There it is. Remember, we named the coordination sphere and everything but the metal first. So it looks like there's only one ligand in here. Don't make the mistake of thinking that's hydroxide. That is actually water written with the donating atom first, the oxygen first. So OH2 is water. Looking back at your chart, you'll see that it's named aqua when it's a ligand. And since there are 6 of them, we're going to name it Hexa aqua. They do not blend. Hexa aqua. And then we'll attach on the chromium, since that's the only thing left. The metal always goes last in the coordination sphere. Now, chromium is one of our sea of unknown charge elements, so it is going to need a Roman numeral. We'll figure that out in just a moment. Then at the end, we have our good old nitrate outside the coordination sphere. It's named like it always is. Now, we have to be able to find charges. So it's important that we know when we have neutral ligands and when they're charged. Water is a neutral ligand, which we should know that water is neutral. Nitrate is a -1, but since there are 3 of them, that's a -3 total. So it looks like chromium is going to have to be a +3 in order to balance that out. So hexa aqua chromium 3 nitrate. The next one's a little bit glitchy. Look at the next one. First of all, there's not anything outside of the coordination sphere. All you have is just that coordination sphere. Looks like we've got tetra, and if you look up CO, you're going to see that it's tetracarbonyl. Nickel does need a Roman numeral. But look at this. This one's weird. CO, carbon monoxide, but as a ligand, it's carbonyl, is neutral in charge. It does not have an oxidation state. So it's neutral, and since it's neutral and the overall species is neutral, that means nickel must be neutral in this case. Well, we haven't ever seen this as part of a Roman numeral before, and actually it's kind of weird, but because Romans didn't have a 0, but nickel is going to have a non-Roman numeral, I guess, of 0 in parentheses. Tetracarbonyl, actually, I left out the nickel part, so let's put that back in. Tetracarbonyl nickel 0. So that is kind of strange. We haven't seen that come up before. Okay, look at the next one. In the next one, mark off the coordination sphere. So we've got the coordination sphere here, and it looks like we've got 2 bromines, and 2 ethylene diamines. If you look back at the chart, notice it's in parentheses. That's our indication that it is a polydentate. So we have to look up those names. But since bromine comes before ethylene diamine, we're going to name it first. So it looks like it's remember what it is whenever it is a ligand, it's dibromo, and we do it in alphabetical order based on the bromine and the ethyl diamine, not on the prefixes. So dibromo. Now, ethylene diamine is a polydentate. So remember we have different prefixes for it. And since there are 2 ethylene diamines, look back up at the chart, it's going to be bis ethylene diamine. The ethylene diamine, when it is written out in the name, is written in parentheses. Ethylene diamine. So dibromo bis ethylene diamine. The only thing left in here is cobalt. No spaces yet. Cobalt does need parentheses. And then outside the coordination sphere, we have our normal old chlorine as the ending of a compound, which is chloride. So dibromo bisethylene diamine, cobalt. Now, what's the charge on this going to be? Well, chlorine is -1. Both of the bromines are -1, so that's another -2. Ethylene diamine, if you look above, is neutral in charge. So it looks like we've got a total -3 for the negative part, so it looks like cobalt has to be a +3. So we've got a Roman numeral 3 again. Another example, in parentheses again, or excuse me, in brackets again, the coordination sphere. So we've got ammonia in there and we've got EDTA. Ammonia becomes amine. EDTA is ethylene diamine tetraacetate, so it looks like the ammonia will go first. Since it's in the monodentate list, we're going to use diamine. And now we're going to write the polydentate EDTA. Since there are two of them and they're polydentate, remember it's bis. In parentheses, go back and look up what EDTA stands for. I'm sure you don't have it memorized yet. Ethylene diamine tetraacetate. Remember, those polydentates have to go in parentheses. Then the only thing left is the copper. We need copper, needs to have parentheses. And then outside of the parentheses is our bromide named, I'm running out of room. Hopefully you can see this all scrunched together, that's bromide. Let's find our charges. Each of the bromines are -1, so that's a -2. EDTA and ammonia are both neutral, so it looks like copper in this case has to be a copper 2. So diamine bis ethylene diamine tetraacetate copper 2 bromide. Wow, you've seen those on packaging and things before, I know, but haven't ever named anything like this before. Okay, brackets again. We've got, first of all, our polydentate EN, which stands for ethylene diamine. Easy to pick out because they're all lowercase. But there are 4 of them, so what's the prefix? Yeah, weird one. Tetrachus. Tetrachus, ethylene diamine. Tetrachus, ethylene diamine, cobalt. And remember, the cobalt is one that must have parentheses, must have a Roman numeral. And then we're going to have nitrate after it, our good old familiar nitrate. So let's see what our charges are going to be here. Ethylene diamine is 0. Each nitrate's a -1, so that gives us a -3 for the total nitrate. Looks like cobalt is a Roman numeral 3 again. Okay, so the next one, we have in the coordination sphere, let's think about the names that we have. We have chloro, we have aqua, and we have amine. Which one comes first? Amine. So this one's kind of long, so I'm going to start way over here. How many amines? It's in the monodentate list, so tetramine. After the amine comes aqua, so it looks like we've just got one aqua, so it's just aqua. So tetramine aqua. Looks like there's just one chlorine, so we don't need a prefix for it. So tetramine aqua chloro. Don't forget the metal. I did that up above, remember? So make sure you get in that cobalt then is the last thing. It needs to be in parentheses. And then on the end, our nice familiar regular way of saying chloride at the end of a compound. We do need, again, our Roman numeral. Each chloride is a -1, so that gives us 3 chlorides at -3. Both amine and aqua are 0 neutral ligands, so cobalt has to be a +3. So that's what's going to go in parentheses. Tetramine aqua chloro cobalt 3. chloride. Our last two are simply, we're going to go backwards and we're going to write formulas for these. So looks like we've got in the coordination sphere, let's see what we've got as far as the metal. Looks like the metal, this ethylene diamine dinitrido, iron. Look, we found iron. Iron's the metal. That's what's going to go first. So we've got iron. And then I just go in order because it doesn't matter if it's in alphabetical order when it's in the compound itself. So we've got bis ethylene diamine. Remember, ethylene diamine is given the symbol little e, little n, and bis stands for 2. Dinitrido, if you look back in on the previous page, nitrido is NO2. And it says there are 2 of them, dinitrido. So we're going to put a 2 after it. And looks like that's all that's in the coordination sphere. So we're going to close the brackets. And perchlorate is our last part of this. And perchlorate is ClO4. Now we need to make sure we come up with what our parentheses should be. We've got iron 3, which is a +3. So iron is a +3. NO2, nitrito is NO2 minus, that's our nitrite ion, and NO2 minus, each of those have a -1 charge, so that's a -2, which means with perchlorate being a -1, looks like we're already balanced and we don't need any subscripts, so that's kind of nice. Our last one on this page is hexaphosphine aluminum sulfate. So our coordination sphere is going to start with aluminum. Hexaphosphine, if you look back at the beginning, phosphine is pH 3. It tells us there are 6 of them, so hexaphosphine. That's it for the coordination sphere, and we've got sulfate on the end. Now let's think about what that's going to do as far as our charges are concerned. Aluminum's a +3, that's an always true, and since sulfate is a -2, remember this green, you don't want to show the green in the final answer. Looks like we've got a situation where we can cross charges, so it looks like we're going to need a 2 after the coordination sphere. We're going to need to put sulfate in parentheses and a 3 after it. Okay, so that's the cations. So what about the anions? The anions are when the coordination sphere is at the end, and the only difference is how you name the metal. Instead of just naming the metal with its normal name, you have to end in an ate. So you have things like aluminate, antimonate, chromate, cobaltate, cuprate, aurate, ferrate, etc. You just end those with their Latin names generally and end with ate. So how does that play out here? Well, this time the first part of it's going to be named regularly. So we've got potassium. Now we've got this coordination sphere. Remember, the metal goes last. So we've got the CN ligand, that's cyano. So looks like we've got tetracyano. And this time we've got copper in an anion at the end. So instead of being copper, it's going to be cuprate. Potassium tetracyanocuprate. Remember, copper needs a Roman numeral. And if you look at the charges, each potassium's +1, so there's a +2 for that. Each cyanide's a negative, so that's a -4 total for the cyanide side. So it looks like copper has to be a +2. So looks like the Roman numeral for that's going to be a 2. The next one, sodium. Now we need the coordination sphere, so we need to name the ligands first. Looks like we've got tetrahydroxo. And now aluminum is in the anion, so it needs to be aluminate. And since aluminum does not need a Roman numeral, it's an always true, we're done. Sodium tetrahydroxoaluminate. The next one, sodium. Looks like we've got 6 hydroxides this time, so hexahydroxo. And now we've got 10 as our last element. And remember, Stan the plumber, this is stanate. And now we need a Roman numeral, so let's see what we come up with. Stan the plumber, it's either going to be a 2 or a 4, so let's see what we come up with. If each of the sodiums is a +1, that's a +2. If each of the hydroxides is a -1, that's a -6. Looks like this particular 10 ion is the +4. So IV for the Roman numeral. Potassium. Named in alphabetical order, we've got cyano and oxalato. So let's go with the cyano first. And we need dicyano because it's a monodentate. Dicyano, but we've got 2 oxalates, and that's a polydentate, so it's going to be bis, remember in parentheses, oxalato, and nickel is nickelate. It does have a Roman numeral, so potassium dicyano bis oxalato nickelate, and it looks like a +4 for the potassium. Each one of those is a +1. Oxalate's a -2, so that's a -4 total for oxalate. Each cyanide's a -1, so that's a -2. Looks like potassium's got to be a +2, or it's not potassium, nickel's got to be a +2 in order to balance that out. Okay, finally, let's do one where we write the formula. We know sodium's first. I know this has been quite the set of notes, but hopefully you've tried to do some of these on your own as we've gone through here. We've got difluoro, dinitrido, stanate 2. So we know that the 10 is going to go here. And we know that it's got difluoro, so 2 F's. Dinitrido, 2 NO2s. So difluoro, dinitrido, stanate 2. So it looks like that's the end of our coordination sphere. So let's look what the charge, or what our subscript should be. If sodium's a +1, and let's see what the total charge is of this coordination sphere. It said it was stanate 2, so 10's +2. Each fluorine's a -1, so that's a -2 total. Each nitrite or nitrido is a -1, so that's a -2. So it looks like this whole coordination sphere is an overall -2. And if sodium's a +1, looks like we're going to need a 2 after the sodium to get that balanced.